A structural component may be perfectly balanced under its external loads and still fail along an internal plane. At one point inside the material, the stresses on the horizontal and vertical faces may be known, but a crack, a weld, or a potential slip plane can be inclined at any angle. The normal and shear stresses acting on that plane will generally be different. Stress transformation answers one precise question. If the stress state at a point is known on the x and y faces, what stresses act after the reference axis rotate through an angle theta? The material point does not change. Only the plane on which we describe its internal action changes. In 3 dimensions, a tiny material cube can carry 3 normal stresses and 6 labeled shear components. Moment equilibrium makes each complementary pair equal. Tau xy equals tau yx, tau yz equals tau zy, and tau zx equals tau xz. Therefore, only 6 independent components define the complete stress state. They are arranged in the symmetric Cauchy stress tensor. Many thin plates, sheet components, and loaded surfaces can be modeled by plane stress. If the faces normal to z are traction free, sigma z, tau xz, and tau yz are 0. The remaining state lies in the xy plane and is represented by sigma x, sigma y, and tau xy. Plane stress is not the same as plane strain. It is a statement about out-of-plane stress components. Before using any equation, we must fix the sign convention. Tensile normal stress is positive. Positive tau xy acts in the positive y direction on the positive x face and in the positive x direction on the positive y face. The opposite faces carry equal and opposite tractions. We now rotate the coordinate axes counterclockwise through theta. The positive x prime axis is normal to the inclined plane, while I prime lies along that plane. This is an axis transformation at the same material point. We are not physically turning the loaded component. Reversing that interpretation reverses the angle sign, which is why formulas from different books can appear different. With our convention fixed, the following derivation and all numerical signs remain consistent. Cut an infinitesimal triangular wedge so that its inclined face has area A and outward normal x prime. Its projection on the x face has area A cosine theta, while its projection on the y face has area A sine theta. Resolve every traction in the x prime direction. The transformed normal force is sigma x prime times A. The sigma x contribution is sigma x times A cosine theta, projected once more by cosine theta. The sigma y contribution is sigma y times A sine theta, projected by sine theta. The two complementary shear tractions contribute 2 tau xya sine theta cosine theta terms. After cancelling A, sigma x prime equals sigma x cosine squared theta plus sigma y sine squared theta plus 2 tau xy sine theta cosine theta. Now use the double angle identities. The result is the average normal stress plus the normal stress difference multiplied by cosine 2 theta plus the original shear stress multiplied by sine 2 theta. Next, resolve the same wedge forces along I prime. The normal stresses act with opposite tangential tendencies, while the original shear stresses contribute through cosine squared theta minus sine squared theta. After simplification, tau x prime y prime equals minus 1/2 of sigma x minus sigma y times sine 2 theta plus tau xy times cosine 2 theta. The sign tells us the actual shear direction relative to the positive y prime convention. To obtain the normal stress on the perpendicular face, replace theta in the sigma x prime equation by theta plus 90 degrees. Both double angle terms change sign. Therefore, sigma y prime equals the average normal stress minus the stress difference term times cosine 2 theta minus tau xy sine 2 theta. Together, these three equations completely describe the rotated two-dimensional stress element. Good equations should survive simple checks. At theta equal to 0, the rotated axes coincide with the original axes. So sigma x prime becomes sigma x, sigma y prime becomes sigma y, and tau x prime y prime becomes tau xy. At theta equal to 90 degrees, the x prime and y prime faces exchange their normal stresses. If sigma x equals sigma y and the shear stress is 0, every plane carries the same normal stress, rotation changes nothing. There is also a deeper invariant. Adding sigma x prime and sigma y prime cancels all sine and cosine terms, leaving sigma x plus sigma y. The trace of the stress tensor is independent of orientation. The center of the normal stress variation is therefore always the average, sigma x plus sigma y divided by 2. A principal plane is a plane on which the shear stress is 0. We can find it by setting the transform shear equation equal to 0. Equivalently, differentiate the transform normal stress with respect to theta and set the derivative to 0. Both roots give the same orientation. Rearranging gives tangent 2 theta p equal to 2 tau xy divided by sigma x minus sigma y. For the correct quadrant, it is safer to evaluate 2 theta p using the 2 argument arc tangent. Substituting this orientation into the normal stress equation gives the principal stresses. Sigma 1 and sigma 2 equal the average normal stress plus or minus the square root of the normal stress half difference squared plus tau xy squared. Sigma 1 is the larger principal stress and sigma 2 is the smaller. Their planes are perpendicular and on a principal element only normal stresses remain. For maximum shear, differentiate the transform shear stress with respect to theta and set the result to 0. This gives tangent 2 theta s equal to minus sigma x minus sigma y divided by 2 tau xy. Comparing this with the principal angle equation shows that the maximum shear planes lie 45 physical degrees from the principal planes. The largest in plane shear magnitude equals the square root of the half difference squared plus tau xy squared, which is also sigma 1 minus sigma 2 divided by 2. On these planes, the normal stress equals the average normal stress. One more design detail matters. Under plane stress, 0 is also principal stress in the z direction. Absolute maximum shear is the largest of the three half differences between sigma 1, sigma 2 and sigma 3. Depending on their signs, it may be larger than the maximum shear visible in the xy plane. For a shear-based design check, compare it with the allowable shear stress. Consider sigma x equal to 80 megapascals in tension, sigma y equal to 20 megapascals in tension and positive tau xy equal to 30 megapascals. The average normal stress is 50 megapascals. The half difference is 30 megapascals. The radius quantity is the square root of 30 squared plus 30 squared, which is 42.43 megapascals. Therefore, sigma 1 is 92.43 megapascals and sigma 2 is 7.57 megapascals. The principal plane equation gives 2 theta p equal to 45 degrees, so theta p is 22.5 degrees. Rotating the element by this angle removes the shear stress. The maximum in plane shear magnitude is 42.43 megapascals and occurs 45 degrees later at 67.5 degrees with normal stress 50 megapascals. Since sigma 3 is 0, the absolute maximum shear is half of 92.43 minus 0 or 46.22 megapascals. This final comparison is important in three-dimensional failure assessment. Strain transformation follows the same rotational geometry, but engineering shear strain gamma is twice the tensor shear strain. That is why gamma xy appears as gamma xy divided by 2 in the corresponding transformation equation. Never copy the stress equations and replace tau directly by gamma. The complete stress transformation map is now clear. Define the sign convention, use equilibrium to obtain the rotated normal and shear stresses, verify the invariance, set shear to 0 for principal stresses, and shift 45 degrees for maximum in-plane shear. In the next lesson, Mohr circle will represent every one of these equations geometrically, including the crucial relationship between theta in the material and 2 theta on the circle.